Welcome everybody, and thank you for joining our new Cards Digital Thursday webinar. The topic for today will be how to improve your warpage with Moldex3D. First, let me shortly introduce myself. My name is Vasco Keizer, and I've been working at Cards for almost 5 years now. I have a background in automotive engineering, and I joined Cards as a technical consultant for the SimCenter 3D portfolio. Currently my role is mainly commercial, focusing on the simulation portfolios, where I'm active with SimCenter and Moldex3D throughout the entire Benelux area. And presenting with me today is Larry Wren from Moldex3D. So Larry, if you could introduce yourself as well.
Thank you, Vasco. Good morning, everyone. My name is Larry Wren. I'm the regional manager for the Benelux and French-speaking area in Europe. I'm very glad to have this opportunity to present to you some typical scenarios where we try to improve our warpage situation. So talk to you later. Back to you, Vasco.
Great, thank you Larry. Looking at the agenda for today, we just had a short introduction. So next we are going to take a look at the basics of shrinkage and warpage and why warpage is so important. Then after that we will have a demonstration in Moldex3D showing a full analysis including warpage. And with that analysis we are going to look at some ways on how you can immediately improve your warpage already within Moldex3D by changing some specific parameters. But let's first real quick start with the basics, so shrinkage and warpage. When we're talking about shrinkage, we are really talking about the shrinking of the product due to the cooling from a molten state to a solid state. But when we are talking about warpage, we are basically talking about an unequal shrinkage throughout the geometry. Now this causes the part to be warped, bended or twisted, for instance. Now this could be caused by differences in temperature, pressure or density distribution and can become quite complex to predict and to improve. Now there are multiple factors that are influencing the warpage behavior. For instance, the material selection, the part design, the mold design with the layout of the cooling channels, and of course the process parameters. Now warpage is in fact a very important phenomenon to predict and to improve, because it has a major impact on the quality of the product itself. Firstly, there's of course the aesthetics of the product. When a product looks warped, bended or twisted, the product will almost have like an inferior look. But besides from the way the product looks, if the product has to be assembled together with other products, it is critical of course that the pieces actually fit together in the way it was meant to be. So dimensional tolerances on holes, joints or snap connections are very important to keep track of. But also consider the structural stiffness and stresses in the part. And take for instance a car bumper that is warped towards the inside. In order to actually fit the bumper on the car, it will first need to be pulled apart to the dimensions of the car in order to fit. Now this will have an impact on the stresses that occur in the bumper. And for the FEA department, it is important to take these initial deformations and possible additional stresses into account when they are performing structural analysis. And for this reason, it is possible to transfer these results from Moldex to FEA software. And this will be a topic that we are going to cover in the next edition of our Digital Thursday. So we've quickly seen what warpage is and why it is important. But how do we actually determine whether we will encounter warpage? This is of course possible by performing a warpage analysis within Moldex3D, where we can easily identify possible causes and try alternate solutions in order to make improvements. Doing this in the software is much more cost and time efficient compared to doing this with trial injections. Even more complex factors like fibers, viscoelasticity, transient effects or in-mold labeling can be considered to get an accurate understanding of the warpage of the part. And by looking at amplified plots or animations of the warpage, like you can see on this slide, we can get immediate insight on how the part will exactly deform, even if the actual deformation will be relatively small. Now one of the important factors that affect warpage, which we are going to see in a demonstration in just a minute, is the importance of cooling. Many times an ideal cooling situation is assumed within injection molding analysis, where the mold is considered to have a uniform temperature. This is easy to set up and gives some quick insights in the filling process of the part. FPW in this case stands for flow, pack, warp, which are the only processes being simulated. However, in a real situation, there will be a temperature distribution in the mold with some hotspots that will have a large effect on the warpage of the part as well. It is therefore advised when looking at warpage to always include a simple cooling layout in order to get a more accurate temperature distribution in the mold compared to when you're using one uniform temperature. So in this case we will be performing a FPCW analysis, or flow, pack, cool warp. But we will see this in practice in just a minute. Now in the demonstration of today we will be building on the webinar that we have done on the 10th of September. There we set up an initial filling analysis starting from NX with the Moldex3D sync module and showed how you can quickly make an adjustment in CAD to improve the filling of the mold. So if you've not seen this webinar, you can watch this back through our website or YouTube channel, or by clicking on the link in the description of this video. For the demonstration of today we will be using the same part, but doing a more detailed analysis including also packing, cooling and warpage. We will show the warpage results and then go over some adjustments we can already try out within Moldex3D to try and improve the warpage. Now for this demonstration I would like to give the word over to Larry Wren. So Larry, if you could take over the screen.
Okay, thank you, Vasco. So we are continuing here from what we had since the last webinar. We have the part ready, the gate runner location ready. We have that extra rib at the corner to help push the air trap to the border so that we don't have a venting problem. And now if we would like to, we can continue to generate a mold base very easily using the mold base wizard. Just like this. You can adjust the dimension if you like to, and then further continue with the coding channels if you wish to. So for example, I can increase the distance between the channels, I can increase the diameter, I can also change the number of channels if I want. So this provides a very easy to use tool for the part designers to have their first experience of what could be a very normal cooling system. So when we have this ready, we would like to ask ourselves, what are the differences between having this or without any cooling channels? We know that a lot of part designers in their workflow, they just consider that there should be an ideal cooling situation, or maybe they just leave this to the mold designers. So they will just run a simulation of flow, pack, and warpage simulation. And we can see that, for example, at the end of packing, if we check the temperature distribution, because we consider that this is an ideal cooling situation, so everywhere on the part surface is exactly the same temperature, which in this case is the mold temperature at 80 degrees centigrade. So in this case, we'll end up with a warpage situation, which looks like this. So 2.8 millimeters at this corner, and then we can also check with the display. This is the final situation, and then with some exaggeration, we can also check that this corner is bending towards the downside, the bottom. And of course, we have some shrinkage, some distortion in the middle, etc. Okay. What if we have used the mold that we just designed using those very simple cooling channels like this? You can see from the screen that our warpage situation has been changed. It is now having the same tendency, just that at the corner this is more severe, so we'll end up with a 3.8 millimeters. You can also make a comparison with the previous situation. The screen will be the previous one. and then you can see that these two, we have on the left the ideal cooling situation, and on the right more realistic situation where we have some cooling channels. And obviously we hope that our mold designers will do everything he can to achieve at least the ideal cooling situation on the left. And then also by common sense, you can also compare the temperature distribution on the surface. So now we'll be comparing with the end of packing situation. So you can see clearly that for the same timing, one scenario which doesn't have any representative cooling channels will be very different than the situation on the right, where we have a realistic approach of the existence of the cooling channels. Okay, so seeing this, the warpage that we had at 3.8 millimeters, we would like to do some improvements. So we will be adding some details to the cooling channels, like this. Continuing from the previous cooling channels, but adding some baffles here, 6 baffles in the middle, adding another loop in the surrounding, and then you will see that the final warpage is still very similar. So if you compare with the previous situation, we didn't get too much improvement from 3.86 to 3.8, and of course the deformation tendency is also very similar. So we would like to take one step further, trying to design the cooling channels, getting them deeper into the part, closer to the part with more baffles, because we saw that the main problem was here, all the heat accumulated in this very big and thick area, so we're trying to cool down this area. But you can see also from the comparison from left to right that actually for that corner it actually got worse. So you can see that starting from a normal cooling channel on the left and then improving to the right by common sense, it doesn't always guarantee that you're making the situation better. When we check further the cooling efficiency, for example, let me get it to the left screen as well. At least we can see that the right scenario, those extra channels, especially this one, is moving also a lot of heat from this small corner here. And then here you can also compare the different percentage of each channel and see how is the performance of your cooling system. So this is something that at least we have tried to do. Okay, so now that we know that these extra channels will not necessarily contribute to the situation, let's try to go back to the simple situation, but then changing the process conditions, especially for the cooling. From the left scenario where we had the cooling result, there was one result that we could sometimes use, which is called time to reach ejection temperature. That means the time that we need for this part to be completely below ejection temperature, we'll have to use 35 seconds, while the original input for the cooling time was at 24 seconds. So the software tells us that actually this is a little bit short. If you want it to be 100% below ejection temperature, then you need 35 seconds. Okay, so that's why we'll just simply take this into consideration and increase our cooling time to 40 seconds, just like this. And then we end up with this kind of warpage. Let me put the left screen again, the original. And now we have a new comparison. So we can see that the warpage has finally improved, so from 3.86 to 3.7 something, and also this central area has a little bit got flatter, like this. At least we see that the bending of this one has improved a little bit. So sometimes we care about the tolerance between these two edges. We want to connect it to another part, because obviously this is the cover of a hand tool, so this might be a little bit helpful for the situation. Or because we know that now we are increasing our cycle time, which in most of the cases would not be recommended for the strategy, because increasing cycle time means that we are increasing the cost of our production. So maybe we'll take the 24 seconds back for cooling time, but instead we will change the temperature difference from both sides. At the beginning, we have used 80 degrees on both sides, so uniform, but in this case, we will introduce a different setting. So here we will use two temperatures for the two groups of the cooling channels. The first group at the bottom at 50 degrees, and the other 6 channels at the top at 90 degrees. So we're creating a 40 degrees difference in those two groups of channels. So you can see the settings like this. Those channels at 90 degrees and the bottom channels at 50 degrees. While in the previous situation, we had 80 degrees on both sides. So you can also see directly from the display in the background that we're finally improved from 3.86 to 3.56, at least for this corner. But again, we can also see that the color of this region has also changed a little bit. So if we put it back with some saturation, then we might not be so happy about this new situation, although we have improved in this corner. So until now, we have already tried many strategies. So starting from a normal loop until a more complex loop of cooling channels, and then maybe increasing the cooling time or changing the balance of the temperature in the cooling channels, but most of them still didn't help too much. So finally, we have decided that we'll not touch the cooling in this case, but instead we'll look at the packing situation. So the original packing was like this. We have used 16 seconds of packing, which was recommended by default by the solver, which we use a guideline from our book which takes the average thickness, what kind of material that you use, the flow length of the material, etc., and then came up with some rough suggestions of a possible packing time. And then here for the packing pressure, because we are not sure what the pressure at the end of fitting will be, so we just take a certain percentage and then gradually decrease over the course. So this is some kind of default value for the packing time. So in this attempt, we will increase the packing time, but in order to be still effective, because we know that the gate will be frozen at some times, so we'll have to see what will be the timing for the gate to freeze in this case. So we can check the log of the packing, which at the bottom you can see that the freeze time of the gate 1 was at 26 seconds. So in this case, we just create a new run on the right, which is 30 seconds of packing. And finally, we see some tremendous difference as compared to the left situation. Let me also put some exaggeration here. So the distance between these two are also much larger, and the deformation at the corner is also much better. At least we have almost improved by 1 millimeter at this corner as compared to the previous situation when we had cooling channel. And of course, if you compare it to the ultimate result in this case, which was the ideal cooling situation, we were also not too far from it. Let me put the exaggeration back again. So at least, although there could be some improvement here, but for the corner, we're already very close. There's 0.1 millimeter of difference. So of course, there could be some other actions or strategies, different trials that eventually we will try to get the part as flat as possible, and then for the remaining part, maybe we'll just try to compensate it from the mount. So that was basically what I would like to present to you today. Back to Basco. Thank you.
Yes, thank you very much for your demonstration, Larry. We've come to the end of our webinar. If there are still any questions, please feel free to contact me through my email address, visible on this slide, vasco@cardsplmsolutions.com. For now, I would like to thank you all for your attention, and I wish everybody a very pleasant day.